Hello guys, in previous video I have discussed Sieve algorithm, and now in this video I am going to discuss modified version of Sieve algorithm, that is segmented sieve. In this video I will be discussing where do we use this segmented sieve and how do we use it, and we will also be discussing its implementation using C++ language. So let's dive into it. So we use segmented sieve when we are given a range. We have to find all the prime number in this range from L to R, where L is smaller than R. So you can say that we can also use normal sieve algorithm here to find the prime numbers between L to R. We can find all the prime numbers from 1 to R, and we will show only from L to R. But there is a problem here, because if I give you the range of L as 10 to the power 10 and range of R as 10 to the power 10, and number of elements from L to R not greater than 10 to the power 5, now you have to create a array of size 10 to the power 10 for using normal sieve. So we cannot create an array of such a large size, it is going to occupy a huge space that is contiguous. So instead of that, we are going to use here a modified version of seal algorithm. Let's see how we are going to do that. So I'm going to do it in two steps. Where first step is I'm going to find all primes from 1 to square root of r. So now using all the primes that I have found in first step, I'm going to use them for marking all non-primes in the range L to R. So similarly, as we have previously marked in normal sieve algorithm, the same technique we will be using here for marking all the non-primes in the range L to R. And we know that why we are marking, how we are going to mark non-primes by using the multiples of the primes. So now let us see how we are going to do that. Now taking an example, so here L is 51 and R is 100, and there are 50 elements in the given range from 51 to 100. So in the case of segmented sieve, we need to create an array of size equal to the number of elements present in the given range. Here it is 50, so we will create an array of size 50, and its indexes will be from 0, 1, 2, 3 till 49, as 50 is its size, so maximum index it can have is 49. So now performing step 1, which says that we have to find all the prime numbers till square root of r. Here r is 100, that is the upper limit of the range, and its square root is 10, so we'll find all the prime numbers till 10. So they are 2, 3, 5, 7. Now in step 2, I'm going to mark all the multiples of these prime number in the given range. So I'm going to take each prime number one by one and mark all its multiple in the given range. So first I will take 2. So for finding the first multiple of a particular prime number, I'm going to divide L, that is the lower limit, with that prime number. If this lower limit gets completely divided by this prime number p, then I'm going to take this number by multiplying it with the same prime number. If it doesn't get completely divisible by p, then I'm going to take the integer part of the quotient after division, this division, and multiply it with the same prime number p, and we will add here the same prime number on which particularly we are working now. So let's do the same with prime number 2. So here I'm going to divide lower limit 51 by 2. So here it is not completely divisible, so I'm going to take only integer part of the quotient, and it is 25. Now I will multiply this quotient with the same prime number and going to add the same prime number, as it was not completely divisible. So now it is 50 plus 2, 52. So now we got the first multiple of 2 in the given range, and it is 52. So starting from 52, I am going to mark all the multiples of 2. So I will mark 52, 54, 56, 58, 60, then 62, 64, 66, 68, 70, then 72, 74, 76, 78, 80, then 82, 84, 86, 88, 90, then 92, 94, 96, 98, and 100. Now after marking all the multiples of 2, I will move on to the next prime number, that is 3. So I will find the first multiple of 3 in the given range. So I will divide lower limit of the range with 3. Yes, it is completely divisible. So 17 times. So I will use this 51 only for starting. So I will start from 51 and I will mark all the multiples of 3. So first multiple is 51, then 54 already marked, then 57, then 60 already marked, then I will mark 63, then I'll mark 66 marked, and I will mark 69, then I will mark 72 already marked, then 75, then 78 already marked, then 81, 84 already marked, then 87, 90 already marked, then 93, 90 is already marked, then I will mark 99. Now I have marked all the multiples of 3. Now I will move on to the next prime number, that is 5 from this list, and I will mark all the multiples of 5 here. So which is the first multiple of 5 in the given range? It is 55. So I will start from 55 and mark all of its multiples. So I will mark 55, 60 already marked, I will mark 65, 70 marked, 75 is already marked, 80 is also marked, I will mark 85, 90 is already marked, then I will mark 95, 100 is already marked. So after marking all the multiples of 5, I will move on to the next prime number, that is 7. So I will manually find out the first multiple of 7 in the given range. So I will divide the lower limit with 7. So it is not completely divisible, so I will use only the integer part of quotient, that is 7, multiply with itself and add the same prime number. So it is going to be 49 plus 7, that is 56. So 56 is the first multiple of 7 in the given range. So I will start from 56, it is already marked, then after this 63 already marked, then 70 already marked, then I will mark next multiple, that is 77. Now next multiple 84 already marked, then next multiple 91, I will mark 91, then 98 already marked. So after marking all the multiples of all the prime numbers till square root of r, I can be sure that the numbers that are left unmarked in the given range are the prime numbers. Now I will iterate through this array and print the prime numbers. But there is a problem. How I am going to map the number with these indexes. So for doing so, I have to do, let's suppose j is the variable which is we are using for marking the multiples of the prime numbers. So we'll mark by using j minus l. So we'll reach the correct index, we'll map each number with its index. So I'm going to mark the status of 51 here at the 0 index. So when j is 51 and I am going to minus l, it is also 51. So it is, its result is 0. So I'm going to mark its result here. And for 52 I will do 52 minus 51, that is 1. So I will write its status at this index 1. Similarly for 100 I am going to do 100 minus 51, that is 49. So for 100 I will mark its status here at the index 49. So now let's see its implementation. So now taking two variables L and R, where L is representing the lower limit of the given range and R is representing the upper limit of the given range. So taking them as input. So now creating a bool type array AR. So its size will be equal to the number of elements in the given range. So we'll find out the number of elements in the given range by the formula upper limit minus lower limit plus 1. So now putting a for loop here to mark all the values in the given bool array as true. So initially I am considering all the values as prime number, and later I will mark all the non-primes and I will make them false. So I till upper limit minus lower limit plus 1 I plus plus and ARI is true. So now declaring a vector here, vector int v. So this is going to contain all the list of the prime numbers till square root of r. So v is equals to sieve sqrt r. So sieve is a function that I'm going to create and it is taking square root of r as its input. So now let us complete this sieve function and later we will complete this main function. So the return type of the function sieve will be of vector int type. So vector int, its name is sieve and it is taking an integer argument. So now in this creating an bool type array, so bool AR, its size will be n plus 1. So we have discussed it in the sieves video. So now again making all the values of this bool array as true, I less than equal n and ARI as true. Now putting here a for loop. So this for loop is going to give me numbers starting from the lowest prime number 2 till the square root of the given number. So inside it I'm going to check if the number is given by the upper loop is prime or not. So by checking it if AR of I is true or not. If ARI is true, it means that it is a prime number. So I'm going to mark all of its multiple. So for I am going to start from the square of I till j is less than equal to n, and j will increase by I as we have to traverse through the multiples of I. So here I am going to mark ARJ as false. So now after executing this for loop, we will have our bool array will contain the status of all the numbers as true and false. Here true index will represent that particular number is a prime number and false index will represent that particular index is a non-prime number. So creating here a vector to store the list of prime numbers, let's name it answer. Now putting a for loop here to traverse through the bool array. So I will start from the lowest prime number and I will go till n given number I plus plus, and I will check if that number is a prime number or not. So if the value of ARI is true, it means that the number I is a prime number. So I'm going to insert it into my vector answer. So answer dot push back I. So now after completing the execution of this for loop, My answer vector will contain list of all the prime numbers till square root of r. So I am going to return this answer. So now at the line number 32, my vector v will receive the list of the prime numbers. So now I am putting a for loop here to get each prime number one by one. So auto I v. So now I'm going to check the first multiple of that prime number in the given range. So for doing so, I'm declaring a variable st for the starting multiple in the given range, and I'm updating it with division of lower limit by the prime number. So let's name this prime, p for prime. So if it is, I'm going to divide it and then again multiply with p. So it will remain, st will remain l divided by p multiplied by p if it is divisible by, if l is completely divisible by p. So lower limit is completely divisible by the current prime number. If it is not, if l modulo p not equal to 0, then we have to add that prime number to the starting st variable one more time. So we will do st plus equal p. So now I have to mark all its multiple. So I will start marking from that st. This is our the starting multiple in the given range. So I will continue till r, and I will progress, my j will progress with that prime number p. So here I am going to mark arj as false. So here I have to do one thing, I have to subtract the lower limit, so I can map that current number with the index of the array, bool array that I have created. So now after execution of this for loop, so my bool array will finally contain the status of each number if it is prime or not. So traversing through it, and so I will start from 0 till r minus l plus 1 I plus plus, and if ari is true, means that number mapped to the index mapped to the number is a prime number, so I will print it. So I'm going to do here cout I plus l, as initially I have subtracted, so here I have to add l, lower limit, to get the correct number. So now this code is completed. Now let's check it by running it. Now I'm providing input as lower limit as 51 and upper limit as 100. So now let's run it. Yes, it is showing, I think it is showing correct number of primes between 51 and 100. So this code is working fine. Hope you understood the concept of segmented sieve. Thank you.